Okay, so thanks for the introduction and thanks for the opportunity to speak here. I'd like to apologize in advance because this is going to be a lot of analysis and sort of very little dynamics. This is joint work with Ana Jouvet from the University of Barcelona, who's sitting right there. And we were interested in studying multiply connected for two components and understand the boundary dynamics, right? But that led us to sort of try and understand the boundary behavior of the universal coverings of such domains. And that sort of got away from us, and that's what I'm going to talk about here. Okay, so first we're going to talk a bit about what's known for Riemann maps, right? And these are sort of the results that we will try and generalize over the course of this talk. Okay, so first, let's say that we have some holomorphic function from the disk to the Riemann sphere, and we take some point on the boundary of the unit disk, right? What sort of language should we use to understand the behavior of this function near that point? Right, and first of all, this would be sort of the best case scenario, right? Because this is an analytic curve. So basically, f is going to extend analytically to some neighborhood of the unit disk, right? And then everything works, everything is magical. But sometimes things are not that good, right? Sometimes you might have like some corners, right? Your curve might not be so nice. And then f is just going to extend continuously to those points, but that's still very good, right? And sometimes your function might be something a bit more complicated. So for instance, this here is the universal covering of the puncture disk, right? So it's going to take these, each of these red circles here, and it's going to map it infinite to 1 onto these red circles here, and it omits this red dot in the middle. And what happens, to understand what happens in this case, we need to introduce some terminology, right? Which are basically the non-tangential limit set, which we denote by f star of e to the a theta, is the limit as f of z tends to e to a theta non-tangentially. What does it mean to tend non-tangentially? It means that you're tending to that point inside a Stolz angle. And what is a Stolz angle? Well, if this is the unit circle and this is ei theta, a Stolz angle is basically a sector, a disk sector centered at ei theta, right? So it's something like this. And we're taking sequences that tend to ei theta inside such sectors, okay? And that is what it means to tend non-tangentially. I'm going to use this notation here, right? And then we have the angular cluster set, which is sort of like the set of all the points on the Riemann sphere that I can reach, that I can sort of tend towards by taking a sequence that tends to a theta non-tangentially, right? So it's sort of the set of accumulation points of the image, as long as I restrict myself to sequences that are going to the boundary non-tangentially. And then there's the full cluster set where I drop the restriction of non-tangential limits, and I just take all the points that I can tend towards by going towards ei theta. Okay, and with that language, the map, right? This map that we had here, right? How does it behave near this point? Well, in this case, it's going to have a non-tangential limit, which is the puncture, which is 0. The cluster set, right, the angular cluster set is a point. It's the same point, 0. And the full cluster set is big. It's the closed unit disk, but we don't really care about that, right? So things are still sort of good. The next case down is something like, let's say, the Riemann map from the disk to this rectangle with these things here that are accumulating on this line. And the thing here is that if it takes a curve something like this, right, then it's going to go. But now we have to sort of avoid all of these barriers here. So it's going to accumulate on this whole vertical line, right? But that's still not too bad, right? Because even though the non-tangential limit is not defined, the cluster set is small and it's sort of under control, right? It's going to be some continuum on this vertical line here. So that's not bad. And finally, things might get very, very bad, such as in this case, which is the universal covering of an annulus. And in this case, what happens is that this red diameter here is mapped infinite to 1 onto this red circle here, right? So as I get close to here, the image is just going to wrap around, 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 around. So the non-tangential limit set is not defined, and the angular cluster set is going to be very big. It's going to be the whole open annulus here. And basically, well, basically anything can happen if you take a sequence that goes towards this point, basically, right? So not ideal. So now what we want to understand is, if you give me some domain and give me its universal covering, how do we know which point falls into which of these cases, right? So how does this work for Riemann maps? Well, for Riemann maps, there's a very well understood theory of what happens in each case. And first, some general good news is that, well, first of all, if you have a sequence that tends to the boundary of the disk, then the image of this sequence tends to the boundary of your domain, right? So in particular, things like this cannot happen for Riemann maps. And second, the non-tangential limit exists at almost every point on the unit circle, right? That's a result that goes back to Fatou originally. So basically, almost every point is going to behave better than that last example that we saw. Okay. And there's also something else, which is a very deep theory of what's called prime ends, which was developed by Theodori in 1913. Right, so which is basically, how does the Riemann map itself see, right, air quotes, the boundary of omega? I'm not really going to talk about the definition of prime ends because that's a whole other talk, right? But it's basically a topological way to answer this question, right? It's going to be some set that sort of represents what the boundary looks like for the Riemann map, right? Each prime end is going to be some maybe degenerate continuum on the boundary. And if you take the domain and add the prime ends, you're going to compactify the domain in a very well-behaved way, right? What does well-behaved mean? It means that it behaves very nicely under the with the Riemann map, right? The prime ends and the Riemann map talk very nicely to each other, right? So the first result, which is due to Theodori, is that the prime ends of omega, which again we are not defining, there is a one-to-one correspondence between the prime ends and the unit circle, right? So the Riemann map sees sort of the whole unit circle as the boundary of omega. And the Riemann map is going to extend continuously to this boundary if and only if the boundary of omega is locally connected. This is a result due to Marie-Thouars in 1921, although it's usually attributed to Theodori. And finally, something else that we can say about the Riemann maps is that the x-axis to a point on the boundary, which are basically homotopy classes of curves going to this boundary point, right? So basically, for instance, if I were to take a domain that looks like this, right? If this is my domain, then this here is one axis because this defines one homotopy class of curves landing at this point. And this is going to be a different axis, right? Because it's a different homotopy class. And there's this correspondence theorem due to Baransky, Fagelia, Jarkin, and Karpinska, which tells us that each of these is going to correspond to some point here on the unit circle where the non-tangential limit of the Riemann map is precisely this point P here, right? So if we understand the Riemann map, we can understand all the different ways to access a point on the boundary and vice versa, okay? And these three results are basically the things that we're going to try and generalize for multiply connected domains here, right? And so now we're going to talk about universal coverings and deck transformations. So first, what domains are we looking at? Well, a domain of the Riemann sphere, right? We say that it's hyperbolic if it omits at least 3 points, right? And for such domains, there exists a holomorphic map from the disk to omega that's called a universal covering, which means that it satisfies some very nice properties. Namely, it is surjective and it has no critical or asymptotic values, right? That's not exactly the definition, but we can think of universal coverings as holomorphic maps that satisfy these two conditions, okay? And if omega is simply connected, this just reduces to the Riemann map. And otherwise, it's going to have infinite degrees. So it's going to be an infinite to one map. Okay. How do we understand this sort of infinite degree? Well, that has to do with what are called deck transformations, right? So basically, if you take some multiply connected, hyperbolic domain and pi a universal covering of omega, then again, it has infinite degree. And there exists this group, right, of Möbius self-maps of the unit disk, right? So one-to-one holomorphic self-maps of D that satisfy this functional equation here, right? So that are sort of invariant for the universal covering. And this group acts freely and properly discontinuously on D, right? Which basically means that you don't have any rotations in this group, 1. 2, this group is discrete, so it's not some kind of continuous Lie group or anything. And it acts transitively on the fibers, which means that for any 2 points, right? So if again, I take the unit disk and I have some universal covering to some weird domain, right? And I take some point P in my domain, and I take 2 points that are on the preimage of P, right? Then I have to have some gamma, which is a deck transformation, right? So which satisfies this equation and takes one to the other. Okay, that's what it means to act transitively on the fibers. And finally, and this is some algebraic topology, this group of deck transformations is isomorphic to the fundamental group of my domain, right? So in some way, it is related to like how many holes this domain has and what these holes look like. So for now, for some examples, because this is all sort of very abstract up to now, we have here some sort of puncture disk, right? And we're going to take a universal covering that's given by, we take a Riemann map from the disk to a half plane, right, to a left half plane. Then we take the exponential that maps this half plane onto the puncture disk. And then we take a Riemann map from here to here that maps this puncture to this puncture. Okay, and if we go from here to here, that's a universal covering. And in this case, well, we know that on this step, the symmetries of the exponential are basically translation by 2 pi I, which when we bring this to the disk, it's going to be some Möbius transformation whose only fixed point is -1, right? So it's a parabolic Möbius map. And all the deck transformations are just the iterates of this Möbius transformation. So they leave these circles invariant. Universal covering is going to extend continuously, and in fact, analytically, analytically because I drew this very nice boundary here. Well, not me actually. Anna made this picture. Thank you, Anna. Right. So the map extends analytically to the whole disk minus this point, and at this point, it has a non-tangential limit, which is precisely this puncture, but the cluster set is going to be the whole domain closure. Okay. Another example that we also saw before, but which I hid from you, is the annulus, right? So we take this guy here, which is some topological annulus. And then, well, we take some uniformizing map that straightens it to a round annulus, right? Some nice round annulus. And we can take a covering of this round annulus from a strip, right? Which is just the exponential. And then we take a Riemann map from the strip to the disk, right? And again, if we just compose all those arrows all the way here, we get a universal covering of this annulus. And in this case, well, the symmetries at this step, which is the only step that has symmetries, are again translations by 2 pi I, right? And when we bring that to the disk, we're going to get some Möbius transformation that fixes -1 and 1, right, and maps this diameter onto itself, right? So it's a hyperbolic Möbius transformation that fixes these 2 points. And it's going to extend continuously. Actually, it's not analytic. I should erase this. To the boundary minus these 2 endpoints here. Okay, again, because I drew this sort of very nice boundary. And what happens at these points? Well, because this curve is going to sort of wrap around this blue curve here infinitely many times, you don't have any sort of non-tangential limits. And again, you have a very big cluster set. All right, so there's basically very little that we can say about the behavior of this map as we tend to these points on the boundary. Okay. Another example, and for this one, I couldn't really produce an image, so you're going to have to use a bit of your imagination. But we have here the upper half plane. Okay, and what are represented here, this region in gray is a fundamental domain for this covering, which is the covering of the Riemann sphere -0, 1, and infinity. This semicircle here is mapped onto the line segment between 0 and 1, and so is this one. And this vertical line and this vertical line are mapped to the straight line that connects 1 to infinity, and this one to the one that maps to that connects 0 and infinity. Okay, and what we're seeing here are sort of some images of these lines under all the deck transformations, which are a very big group. It's this guy here. It's called the principal congruent subgroup, yada, yada, yada. It's big. It's a very big group. And because you have like copies of these circles getting smaller and smaller and smaller and accumulating everywhere on the real line, our universal covering has no continuous extension to any place on the real line, right? And the limit and the non-tangential limit exists only at countably many points. And at each of these points is going to be either 0, 1, or infinity, right? So one of the 3 punctures. So this here is sort of the worst case scenario of what a universal covering could look like, right? So it could look very bad. So what exactly are the questions that we're going to try and answer for the remaining, let's say 35 minutes, right? So if you give me a hyperbolic domain and a universal covering, I want to know first, how should I define the prime ends of omega, and what do they correspond to on the boundary of the disk? Under what criteria do I have some continuous extension to maybe some subset of the boundary? And finally, if I have to access some point on the boundary of omega, how do I find these accesses on the unit circle? Right? And remember that these were sort of the 3 main theorems that we had for Riemann maps. And what we're going to try to do is to find basically multiply connected versions of these results. Okay. So now let's get to it. But first, does anyone have any questions up until now? No? Okay. Okay, so in order to answer these questions, we're going to have to look at the universal covering from a few different perspectives. Right, so first let's talk about limit sets. Okay, so we had this universal covering, and we said that we have this group that's called the group of deck transformations. Right, and now for some point on the unit disk, we're going to take basically the derived set, right? So the accumulation points of the orbit of Z under this group, right? So basically, I can take I can take, let's say, 0, right? And then I start applying my deck transformations, and I'm going to get a bunch of points here. But because the action of the deck transformations is free and properly discontinuous, the only accumulation points of this thing are going to be on the unit circle, right? So in here, I'm just going to have a bunch of discrete points and a bunch of accumulation points on the boundary. And because of, well, how the hyperbolic geometry of the disk works, I will get the same set regardless of which point I pick to start sort of iterating. So and we call this set, right, this set lambda, the limit set of gamma. And there's a lot of literature going on with limit sets of groups like these, right? These are called Fuchsian groups, and more generally Kleinian groups. And people are very interested in things such as how many fixed points do I have in this group? What's the Hausdorff dimension? What's the area? There's a lot of research that went on and is still going on regarding these groups. Okay. But this group is a bit sort of big for our purposes, right? So there's a subset of this guy, which was introduced by Hedlund in 1936, which sort of goes like this, right? So we take the limit set, and we take some subset of this guy, which consists of the points in the limit set where some subsequence of my orbit is approaching non-tangentially, right? So in this drawing that we have here, it will be something like, I can find some subsequence of all these points that I drew here, right? And this subsequence is standing somewhere non-tangentially, right? So it's staying inside one of those nice disk sectors that we saw before, right? And let's say that this is this guy here, zeta, and this guy is going to be a point on the non-tangential limit set. And again, basically by the same argument as before, I will get the same set regardless of which base point I pick for calculating the orbit. And we're going to call this guy the non-tangential limit set of my group gamma. And a very nice result about this guy, I'm not sure who first proved this, might have been Hedlund, is that this set always has either 0 or full Lebesgue measure on the unit circle. But the same is not true of the big limit set, right? The big limit set might have some partial measure on the circle. Okay. And this is going to give me a partition of the unit circle into 3 distinct bits, right? The first bit are the points that are not on the limit set. And I'm going to call those guys regular. Yeah. Let's see. Is it? It's no, not very clear. But it is true in general, and you can use some sort of normality arguments to show that it's non-empty and that it is in fact generally quite big, right? Because you have the 2 easy examples that we saw before, right? The punctured disk and the annulus, right? So let's see if we can go back all the way there. So like for in this example, right? Remember, this was the whole group of deck transformation. So the only point on the limit set is this guy, right? Because the orbits are all going like this, and they go back to this point. This guy, well, we have this group of deck transformations. So the orbits are sort of going on this blue line here. So the limit set is going to be 1 and -1, right? So these are like the small limit sets. And if I take any other domain that is not simply connected, the limit set is going to be either a Cantor set on the unit circle or the whole circle itself, right? But that I cannot, like off the top of my head, think of a very short argument why. Okay, so now back so we have this partition, right? We say that the points that are not on the limit set are regular. And then we have the two limit sets that we saw before, right? So the non-tangential limit set and the tangential limit set, which is basically the limit set minus the non-tangential limit set, right? So we have broken the unit circle into 3 bits, right? The regular points, which because the limit set is always either Cantor or the whole circle, the regular set will always be open, and the other two will be something else, right? And that's one way to look at the universal covering and what it's sort of doing on the boundary. Yep. Exactly.
As one element, then I think it is conical element set.
Exactly. Exactly. Yeah. Which might be small, might be a lot of points. Since Felix mentioned that, let's go back to these examples that we had before, right? So in this one, well, because the orbits are tending to the limit set, which are these 2 points along this blue line, right? 1 and -1 are both on the non-tangential limit set, right? So in this case, the limit set equals the non-tangential limit set. And in this case, right, because all the orbits are following these circles here, they're called horocycles, they're all tending to this point tangentially, right? So in this case, the non-tangential limit set is empty, and you're just left with, the tangential limit set. But for every other example, again, other than these two, you're going to have a limit set and a non-tangential limit set. Okay, so now another way of looking at what the universal covering is doing on the boundary is to try and follow the images of the radii. Right, so I take my universal covering and I look at where my universal covering is sending the origin. And in the hyperbolic metric of the disk, sort of the geodesics, the hyperbolic geodesics that are emanating from 0 are going to be the radii, right? So in this example that I do here, let's say that this is the origin, right? And the geodesics are going to be things like this, right? So spokes on a wheel, basically. And because the universal covering is a local isometry of the hyperbolic metric, the hyperbolic geodesics in omega that are emanating, air quotes, from P are exactly the images of these guys, right? And now the question is, what are these images doing, right? So one possibility is that as R tends to 1, right? So as I approach the boundary following one of these spokes, the image is also escapes to the boundary. That's sort of a very safe option. And we say that this guy, right, this point e to the I theta, which would be this guy here, is of escaping type. Another option, which is the exact opposite of this one, is that as I follow along, the image of this guy remains compactly contained inside my domain, which is the case, for instance, if this maps to some closed geodesic, right? So something like this. And I say this, and then in this case, we say that this guy is of bounded type, which is bad. We don't like these guys. And if it does neither of the above, we say it's of bungee type. Bungee here in honor of Dave Sixsmith and John Osborne, who studied what's called the bungee set in complex dynamics. And this, well, any point on the unit circle is it has to be of one of these 3 types, right? So this gives us a second partition of the unit circle into 3 different categories, okay? And now we're going to try and put these two things together and see like which points correspond to which ones. Just to recap, right, we had the classification according to the limit set, which was regular, non-tangential, and tangential points, and the images of the geodesics, right, which are points of escaping, bounding, and bungee types, right? And the question is, which ones correspond to which ones? And the answer is, it's not exactly these three with these three, but there is an answer. And our main theorem that Anna and I proved is that it goes like this, right? So the rows of this table are equivalent, right? So the points of escaping type, which are the nice ones, are basically the unit circle minus the non-tangential limit set, right? So we throw away the non-tangential limit set, and everyone that remains sort of does nice things in the sense that if we follow the radius that lands on these guys, the corresponding geodesic is escaping the domain. Then, well, to find these two guys, we have to take the non-tangential limit set and break it apart into the points that belong to finally generated subgroups of the non-tangential limit set, and the ones that do not belong to any finitely generated subgroup. And the first one is going to be the points of bounded type, and the second one is going to be the points of bungee type. If that does not, oh, sorry, question? Sorry?
Is it subgroups?
Yeah.
Of
Transformations.
Basically, well, yeah, you can think of them like these guys as being the points that belong to, let's say that they belong to the non-tangential limit set of some finitely generated subgroup of the deck transformations, right? And these guys will be the ones that do not belong to any to the non-tangential limit set of any finitely generated subgroup of the deck transformations, which is a bit of a mouthful, but it will make hopefully more sense in a bit. I had something to say, but I forgot. Anyway, so now let's sort of delve into each of these types of points and try to understand a bit more what the universal covering is doing and why we're seeing those points there, right? So let's look at points of escaping type, which were the nice ones. Why do I say that they're nice? I say that they're nice because if I take a point of escaping type, then there exists some unique component of the boundary of my domain such that the angular cluster set of my universal covering belongs to this boundary component, right? In other words, let me try and make a new drawing. Do we have any colors here other than white and green? Should be red and blue. Ooh. Ah, found them. All right, so now I have colors. Okay, so now let's say that I have this guy here, which is some escaping point for the universal covering of, I don't know, let's say that this is my domain, right? Where here I have some sequence of points tending to these boundary components. And if I take this guy and is of escaping type, then there exists one of these components, let's say this one, such that anything that happens sort of like non-tangentially here is going to be contained sort of like very close to this boundary component, right? So in some sense, the image of this point belongs to this boundary component, right? In some sense, I'm not making this very precise because doing that would require us to talk about prime ends and impressions of prime ends. But in some sense, you can sort of say that the universal covering is mapping this point onto something that belongs only to this boundary component. Okay. If the boundary component in question happens to be a point, right? So a boundary point, then so let's say this one, then I actually have a non-tangential extension of the universal covering to I theta. The limit has to be this isolated puncture. And this guy, and this guy is going to be the fixed point of some parabolic deck transformation, right? So there exists some parabolic deck transformation that fixes this guy, right? Something like this. Otherwise, right? So if this is not the case, and this boundary component that is sort of capturing the angular cluster set is not an isolated puncture, right? So in the case that I had drawn before here, right? So if that goes to something here, then this guy has to be, wait, that's not right. That's not right. Okay, so ignore this item. And another very nice thing about these guys is that they sort of have everyone covered, right? In the sense that for every component of the boundary, I'm going to find at least countably many points on the unit circle, which are of escaping type, and whose angular cluster set belongs to this boundary component, right? So over each component of the boundary, I'm going to find at least countably many points here that are sort of quote unquote mapped to this boundary component. Okay, but again, ignore this bullet point here. This is wrong. So now that we saw the nice points, let's look at the bad ones, right? So if I take a point that's of bounded type, then these guys sort of come from finitely generated geodesics. What do I mean by that? I mean, let's say that this is my domain, right? And now I'm taking some finite subgroup of the fundamental group, right? So let's say I'm gonna pick this closed geodesic here, and I don't know, this closed geodesic here, right? And I'm going to start taking sort of like combinations of these two. So I take a curve that's gonna go around this one once, then around this one another time, and then around this one another time, and then back to this one, and so forth and so on, right? But as long as I stick to these two sort of words made of these two red guys, I'm going to find some point here such that this radius is sort of mapped onto some geodesic that's going to follow this itinerary that I prescribed. And this point is going to be of bounded type, right? So in this sense, these points, which were the bad ones, sort of describing the finally generated geodesics of my domain. And because these guys are of bounded type, we can show that as you approach this point non-tangentially, things can get very messy, right? Because you have this geodesic and you have some stuff that's sort of nearby. So the angular cluster set is going to intersect the domain, right? These points are not mapped to the boundary of the domain, right? And unless my domain is doubly connected, right? So if the connectivity is at least 3, then I will have uncountably many points of this type, right? Because there will be uncountably many different ways that I can combine things here. Okay. So which is sort of bad news, right? Because this means that in general, it will have quite a few bad points. And finally, the guys of oscillating type, I mean, if I talked about the good points and the ones that come from like finally generated geodesics, then these guys are in some sense the infinitely generated geodesics of my domain, right? In the sense that, let's see if I can, I'm not sure I can make this drawing, but let's try. Right, so in this case, in this domain that I drew, I have like I have all of these holes, right? Infinitely many holes to choose from, and they're tending to these big boundary components. So I can take like infinite sequences of elements of the fundamental group, right? And I could maybe try to find a geodesic that follows along this itinerary. So it goes like this, and then it goes like this, and then it comes down here, and it does something like this, and then it goes up, and then it goes back to this guy, right? So it's going to be some sort of geodesic that winds around, that keeps like oscillating between going around some of these guys, then around some of these guys, then around some of these guys, and so forth and so on. Right, so it's some kind of oscillating geodesic in my domain, right? And because it has to do this oscillation, right? Because it has to like cross this region, let's say this region here, infinitely many times, I will also have some non-empty intersection of the angular cluster set with my domain, right? So these guys are also not, let's say, points on the boundary, right? These guys, right, the points of this type, they're also not mapped to the boundary of my domain in some sense. And because of how I have to do the winding, these guys, right, the points of oscillating type, you're going to find them sort of only around non-isolated boundary components of omega. Okay. And also, if I have some non-isolated component, like say this guy, I can construct uncountably many of these points whose cluster set intersects this boundary component. It's not contained on that boundary component, but it contains that guy. Okay. So this was all very sort of hand-wavy, but if you have been sort of somewhere else for the past 15 minutes, the important bit is that in some sense, the pre-image under the universal covering of the boundary of my domain is going to be the unit circle minus the non-tangential limit set, right? These guys are, in some sense, right, quotes here because we still haven't talked about prime ends, these guys are the boundary of my domain as seen from the unit circle. And this set here is going to contain both the regular points and some singular points, right? Some points on the limit set that are lying over non-isolated boundary components. And because of this guy is very nice, it means that this boundary always is either empty or full measure on the unit circle. And a very short idea of the proof, it involves something that was introduced by this guy, Otsuka, in 1954, which are ways to exhaust a Riemann surface by sub-Riemann surfaces, right? So we start with this. Then I put a Riemann surface in here, right, which has a much nicer boundary. Then I take a second one that contains the first one. Then I take a third one that contains the second one, and so forth and so on until I exhaust the domain, right? And this guy, Otsuka, he spent some considerable time trying to understand what this would look like on the boundary of the circle. And the second ingredient is what I called hyperbolic Stolz angles, which are hyperbolic formulations of those sectors that I showed before, in terms only of the hyperbolic metric. And these are introduced, best as you could tell, by Bearden and Kahn in 2008. Right, and it basically means that you take some geodesic ray that lands at your point, and they're going to take the set of points at some finite hyperbolic distance from this guy. And what you can show is that these sets that you get, they're sort of equivalent for all intents and purposes to the classical Stolz angles. And if you combine these two things, you can get a sort of full version of the table that we had before that has a third column that comes from the exhaustions that we saw before. And the trick of the proof is we're going to show that these, this column is equivalent to this one, and this one is equivalent to this one. But that's all very technical, and I have 5 minutes basically. So some immediate consequences of this, actually I think I will skip this bit because there's more interesting stuff ahead. Right, so now let's talk about some accesses to the boundary, right? So how am I going to get to a point on the boundary of my domain? Right, so we say that a point on the boundary is accessible. I mean, if I can find some curve in my domain that lands there, right? So that the limit is exactly this guy. But now, since I have a lot of boundary components, I can say that a component of the boundary is accessible if there exists some continuous curve in my domain such that the landing set belongs to sigma. What's the landing set? It's basically the set of all accumulation points of the curve, right? So like a curve that does something like this, for instance, the landing set will be this boundary component. And an immediately corollary of the theorem that we saw before is that all the boundary components of any hyperbolic domain are accessible. Which means that if I have a domain that's something like this, right? So the Riemann sphere minus a bunch of reefs and minus the origin, right, this red dot here is accessible, right? There exists some curve in my domain that avoids all the reefs and lands at this point. But at the same time, I can have something like this, which is the same example, but now the point has become an interval. And now even though this interval is an accessible boundary component, right? So there is some curve that avoids all the reefs and accumulates on this whole red interval here. None of the points on this line segment are accessible because any curve that goes towards this guy has to avoid all of these reefs. Okay, so even though every boundary component is accessible, I can have a component that is made up of only non-accessible points, which we found very nice. And now how does the whole correspondence theorem look like in this setting? Well, we said before that an access to a point on the boundary of a simply connected domain is going to be some homotopy class with fixed endpoints of curves landing at this guy. But using this definition here brings some problems, right? Because for instance, if I take the annulus and I take this point on the boundary, I can take this curve, and they're not homotopic, but they should be the same axis, right? I'm accessing this guy basically from the same side of the boundary. But if my domain looks like this, right, it has a bunch of holes going off to infinity, and I have these two curves here, these should define different accesses to let's say infinity, which is like all the way up there, right? So we have to ignore some bits of homotopy, but not all bits of homotopy. And it turns out that the right definition of access, 1 minute, okay, is that we should take a homotopy class that fixes only the point on the boundary. And if you use this definition, then we get a correspondence theorem that is basically, well, what you expect, right? The set of all accesses to a point is equal to, let's say, the preimages of this point sort of ignoring homotopy, right? So quotient the deck transformations. And I am told I'd have like no time. So we should skip all of this other stuff. And just leave the summary here. Thank you.
Have any questions? Woman. More than.
Ooh.
More than who?
I don't know who raised their hand, but please.
Yes.
So I wonder what kind of open questions remain here.
So one big open question that is just
This is, we said before that on the unit circle, you're going to have the regular points, but you're also going to have some singular points, which are of escaping type, but which sort of correspond to non-isolated boundary components, right? And we have this whole theory of prime ends that I didn't get to talk about. And one of the big questions is, like, if I take a point that's here, whose prime end is sort of this, whose impression of the prime end is sort of this boundary component, what does the angular cluster set look like in general? And other questions which are more dynamical in nature are, can we use this theory, talk about boundary dynamics in, say, an infinitely connected Baker domain, which is why we did all this in the first place, actually.
I just wanted to say, if you wanted to use your 2 minutes for questions to give us your favorite consequence that you had to skip. Short favorite.
Okay, so so let's see. One of my favorite ones, which is the only dynamical one that I have on this list, is that if I take any meromorphic function and the sum for 2 component of this guy, then the boundary of this component always has positive logarithmic capacity, right? We knew this for the whole Julia set before. That's a result by Gwyneth. But now we know it for the boundaries of individual for 2 components. And something that I think is true, but I thought of the proof like yesterday on the bus to the airport at 3 a.m. So take this with a pinch of salt, is that, well, because it has positive logarithmic capacity, it's going to have a harmonic measure. And what seems to be true is that this measure has to be supported on the whole boundary. Okay, so these are some cute little dynamical applications.
Nothing.
Sorry. Nothing. Then anybody else would like to ask? Yes, please.
Just maybe a pointed question. So if you generalize this theory, not maybe to from Riemann maps to the coverings, but in the direction, if you consider not some quasi-conformal images of simply connected domains. So is there anything possible to say about this?
That is a very good question. Probably, but I do not know what exactly. But I would guess that a lot of people have thought about these things before. But I don't know. Sorry.
Any other questions? If not, then thanks, Gustavo, Rodrigues, Ferreira.